Sì, professore.
Grazie. Okay, we can start with the lesson of this afternoon. We had 2 reservations for the room today, but nobody was coming, so I am back in my office again. And this is the reason of these few minutes of delay. So let's share the screen so we can start. Okay, just one moment. Okay. Okay. So we can start with the topic that I want to discuss with you, which is related to the class we have mentioned many times of the ceramic materials. And my purpose is to discuss with you in a deep way with respect to what we have done in I would say, very few passages in the last course, this class of materials, in order to let you know which are really the applications in the area interesting for us, and which are the limitations of this class of materials from a structural point of view, then turning to discuss in another lecture about the concept of ceramic composite materials. So let's start with a bit of etymology. The term ceramic is derived from a Greek word, keramos, which means baked clay or pottery, essentially. And what are they? They are inorganic, non-metallic materials, which are made essentially by a metallic and a non-metallic elements, bonded between them by ionic and or, that depends, as we will say in a few moments, covalent bondings. So the amount of ionic bond or covalent bond, as we know, that depends on the difference of electronegativity between the 2 elements. So for example, if we are going to take, as in the table, one oxide which is called magnesium oxide, made by 1-to-1 atom of magnesium and oxygen, where the bonding is between magnesium and oxygen. Well, these 2 elements, they do have quite a relevant difference in electronegativity, so thus results in more or less 70% of ionic character of the bonding, being the rest, 27-30%, as covalent character. If we are focusing on another, which is a non-oxide, for example, the last one, silicon carbide, made by 1 atom of silicon bonded with 1 atom of carbon. In this case, the electronegativity difference is quite low, and so essentially, or mainly, if you want, the character of the bond is covalent to something which is near to 90%. So we do have more ionic or more covalent, but in any case, no metallic bonds, depending on the electronegativity difference. Which are the main properties for which these classes of materials can be interesting for some of our applications? Well, that's at a glance one of the, let me say, most comprehensive resume of the properties of ceramic materials. Then each ceramic materials will have its own properties, and we can say, generally speaking, that They are materials, solid materials, having a high melting, or in some cases, that depends on the reactivity, decomposition temperature. So if we focus on melting temperature, they are materials with very high values of melting temperature. Due to the bond between the atoms, they do have also high elastic modulus. Generally speaking, the Young modulus of ceramic materials is higher than that of metallic materials, and obviously of polymeric materials also. They are very hard materials, so they have high hardness, measured according to the standard testing that we already know. We say that they have, to some extent, a low chemical reactivity. We could say a reduced chemical reactivity. Why we need to specify this? Because if we are thinking to chemical reactivity of any material as the possibility that this material is going to interact with the working environment, that is, for example, going under corrosion phenomena, we should and we must remember that talking about corrosion of materials, we do have two broad classes of corrosion phenomena. The first class is that based on the so-called electrochemical corrosion, where exchanges of charges, electrons and ions is going to happen. This class of corrosion phenomena includes flowing of current density, and is the class of corrosion phenomena which is going to happen when we do have condensed solution. That is, for example, at room temperature in standard condition. The second class of corrosion phenomena is the class which is also called high temperature corrosion. That means we do not have exchanges of electric charges. We do not have electrons flowing through the corrosion circuit, but we do have direct chemical reaction between the elements. And this happens when we are usually at high temperature without condensed solution. So if we remember that ceramic materials, due to their bond, non-metallic bonding, they are insulating materials from an electrical point of view. This is the reason because of we can say for sure that ceramic materials cannot undergo under electrochemical corrosion. The question is, can they be subjected to high temperature corrosion? And here the answer is yes, but that depends on the working environment. So when we say that they do have low chemical reactivity to our purpose, we are going to say that they are not subjected to electrochemical corrosion. They could be subjected to high temperature corrosion, but depends on materials composition and on the working environment. Due to the fact that they are hard material, we can also expect, and this is true, that they have a good resistance to wear, that is, a good resistance to tribological applied loads. If we move, looking a little bit to the, generally speaking, to the structural properties, we do have some weak point of these bulk material, ceramic bulk materials, because they are very brittle, so they have very low values of fracture toughness, something which is around 2, 3, 4, that depends on the materials, megapascal per square meter. Please remember that when we are talking about, for example, structural aluminium alloys for use in aerospace fields, we have something which is around 40 megapascal per square meter as fracture toughness. So here we are at least at one order of magnitude less. So they are very brittle. They are not tolerant to pre-existing defects, which can easily propagate when we do have tensile stress applied. They are brittle, so they have also low resilience. That is, they are not going to resist to impact applied loads. And if we have in mind the concept of resilience, which is, I remember to you, measured on a lab scale with a standard test, for example, of Sharpie or ISOT, well, here we have values of resilience of the materials, that's the capacity to absorb energy under impact, which is very, very low. And in terms of figure, the resiliency is something equal to 0, comma 0 some figures for the materials itself. Then, if we combine the insulating properties, that is, they are not thermally conductive materials, generally speaking, if compared to metallic materials. And if we combine with this aspect also the poor resistance in terms of resistance to tensile loads, we can expect, and this is true, that from a structural point of view, we have is related to the fact that they do have usually a low mass density value. The figures of mass density at a glance, then again, each ceramic materials will have its own data, but at a glance, the mass density of the ceramic materials is something which is very near to that of aluminum alloys, because it is around 3 grams per cubic centimeter. So if you remember when we discussed about aluminum alloys, again, some years ago, we have called these alloys as light alloy, light metallic alloys, to stress the fact that the mass density is low, is something around 2.7 grams per cubic centimeter, and the same applies. I mean, they are light materials for what it concerns ceramics, being their mass density very near to that of light aluminum alloy. This is just to point out some general concept which can be applied to ceramic materials. Then I specify again, each ceramic materials will have for each class of this property its own data, but the concept that we have defined now can be considered valid for all the class of ceramic materials. The high temperature melting becomes a rise. I don't want to be inside this, which is something you have seen in chemistry at the first years of your course of study, but in any case, is related to the bond energy. Higher is the bond energy, higher is the melting temperature of the materials itself. And this bond energy is related to the equilibrium bond length between atoms, which are the constituent atoms of the materials we have in mind. And the bond energy of the bonding, ionic or covalent, depends on the percentage, is higher than that of a metallic bonding. So we can expect, and this is true, and this is verified, that the melting temperature of the materials is ceramic is higher than that, generally speaking, of metallic alloys. We do have a special class belonging to the ceramic area on which we will not have any discussion, just a recall now. And I recall because they are very important, for example, for our industry, I mean for the Italian industry. We do have many ceramic districts in Italy contributing to the Italian economy in a relevant way. Which is the class of the traditional ceramic. Why we will not discuss about traditional ceramics? Because they are not used or potential candidate for application which are interesting in our sector. But in any case, just to let you know, the traditional ceramic, which can be used, as you see here, for example, for bricks, for roof tiles, for wall tiles, for tableware, for fire bricks for furnaces, for example. Then we have also the classes of glasses as abrasive or as cements. They are fabricated starting from natural existing raw materials such as clay minerals and quartz sand. Then they do have specific fabrication technology, which are full of technical, let me say, knowledge, but they do have a property which is going to make them different from the materials ceramic that can be interesting for us, which is the porosity. Because when we talk about traditional ceramics, usually we do have a level of internal porosity which are around, sometimes can be higher, sometimes can be lower, but around 10%, which is a quantity not suitable for us when we want to discuss the possibility to use these materials as materials for structural components. But anyway, traditional ceramics, I repeat, they are very important for the Italian economy, and they are also known worldwide, but they are not interesting for our application. What is interesting for our application is the class of the so-called advanced ceramics. The advanced ceramics, which has also, they do have also a standard definition from ISO or the American Society of Testing All Materials. They define the advanced. They are also called technical sometimes ceramics, or fine ceramics, or engineering ceramics, or synonymous, where we are looking to, first of all, materials having very low value of porosity. And this is related to the specific fabrication technology which is used to fabricate components starting from the raw materials. Then the raw materials are usually synthetic raw materials, that is synthesized in the laboratory, obviously at an industrial level. But they are still, again, belonging to the general class of ceramics that is predominant non-metallic, as we have seen at the beginning, and inorganic materials, but with specific functional properties, with specific functional attributes. And so we can find in this class of the advanced ceramics, which can be interesting for us, materials belonging, as it is stated on this picture, but I will be more clear in a moment, belonging to different subclasses of ceramic materials, potentially used for optical application, for thermal application, like, for example, burner nozzles, crucibles, isolation parts, or heat exchanger. For mechanical application, like, for example, cutting tools, wear parts, engine parts, but I will be clear here because in this case, we do have some evolution looking to ceramic composite materials. Actually, when we talk about ceramic used in engine parts, we are talking about coatings, materials that we will recall today, but we have met many times, that is partially stabilized zirconia, for example, made by plasma spray. Or we can have also application for chemical purposes by relying, as we said before, on the fact that electrochemical corrosion cannot happen with ceramic materials. So insert in pumps, filters, in order to protect from corrosion and from wear, relying on high hardness of the materials itself, as well as other applications, important, not, let me say, belonging to the field of our interest, I mean, of the interest in of our courses, like nuclear applications, shields, absorbers, or electromagnetic application. Here, just one thing we can recall, which is the possibility to use, as we have already stated in one of our lectures, piezoelectric ceramic materials, which are used, for example, for sensors to be adopted when we have to monitor, for example, impact loads. We can divide, and we can be quite simple here, the classes of the ceramic materials into, first of all, oxide-based materials. Oxide-based materials, this means that we do have the metallic element, which is, for example, like in the slides, aluminum, but the non, or titanium, but the non-metallic element is always oxygen. So oxide ceramic, advanced ceramics, belong to that class in which the non-metallic element is oxygen. We can have mixed oxide also, in which we do have not only one metallic and oxygen, but, for example, a couple of metallic and oxygen. And this is the case of mullite, of spinels. Spinels, we met them when we discussed very rapidly about materials having RAM or radon properties. Then, when we have the non-metallic element, which is carbon, we have the classes of carbides. When it is nitrogen, we have the classes of nitrides. When we have boron, for example, we have the classes of borides. So we can say that we can divide the ceramic, advanced ceramic materials in oxide materials and non-oxide materials. Inside the non-oxide materials, we can have carbides, nitrides, and borides. For what it concerns our application, as you will see, but as you can also realize by looking to this, we do not have, let me say, talking about the application, which can be interesting for us, always is, we do not have a very wide choice of advanced ceramics to be proposed. If we compare, for example, these classes with the class of the metallic alloys, you remember in the metallic alloys we can have the aluminum-based, titanium-based, magnesium-based steels, nickel-based, cobalt-based, that is the class of superalloys, iron-based superalloys, and so on. Here the choice is very restricted, but nevertheless, some interesting applications and the necessity to know which are the basic properties of the materials exist. And this is the reason because of we are going to discuss about that. Before going inside, let make some examples of application. The first one was recalled many times, and today we will put online some concept in order to let you to well remember the importance of the so-called thermal barrier coatings. Thermal barrier coatings, which are used as coatings in the whole part of the engines, and usually they belong to the class of the oxide ceramic materials. I will not say advanced ceramic each time. We are now discussing only about advanced ceramics. So I should say oxide-based advanced ceramic materials. I just say for the simplicity oxide-based ceramic materials. The application in this case can be extended also to, let me say, thermal protection systems, for example, in rocket exhaust cones, insulating tiles as those flying some years ago with the space shuttle, some other applications as you see here. And in this second area, usually the attention thing, for example, to the space shuttle, that is to thermal protection system, but we will see also other example, is focused on non-oxide ceramics, like those based on silicon carbides, essentially in the form, and this was the solution of the space shuttle tiles, the insulating tiles of the space shuttle, in the form of ceramic matrix composites. Also some discussion, some activities with this class of materials is running for use in jet engine turbines as materials for blades. And I will show to you some niche examples, even though the standard solution still is the use of the super alloy. When we are talking about the possibility to use a ceramic material inside, in the form of composites, inside engines, well, we can understand quite easily which is the ratio of this purpose. We remember that in this case, let me say, one of the most important point, one of the most important item to be satisfied is fuel efficiency. In the fuel efficiency, since we would like to let the engine work at the highest possible temperature without melting, for example, the blades, or reducing the requirements of intercooling in order to let me say, the working temperature suitable with the material selected. And when we move conceptually through the class of ceramic materials, we are thinking about materials with a formulation which could work at temperature as high as 1500, 1600 Celsius, which is 500 or 600 higher than the working temperature of standard and nickel-based superalloys. And this means that we would increase the energy efficiency by using, for example, less fuel, or by having a higher payload. And this is the reason because of there is interesting also in engines for this class of materials. So if we rise the temperature in turbine, that means that if we have higher temperature on the combustion chamber, we do have an improvement of the thermodynamic efficiency of the thermodynamic cycle, as you should remember, and this will improve the overall efficiency or yield of the cycle itself. In this case, the most known solution is, and so we are going to talk about the possibility to use ceramic now in the engine, is related to the use, as I mentioned to you, of the so-called thermal barrier coatings. And that is essentially a protective ceramic overlay on the blade, for example. Let's have this example. They are also used in the combustion chamber in order to have the possibility to limit the working temperature of the nickel-based superalloys to 1050 Celsius or 1090 Celsius. That depends on the design philosophy, the USA or the European one, which is considered the highest temperature, the highest working temperature of a nickel, of a most performing nickel-based superalloys, in order to have suitable creep resistance of the materials itself. So first, let me say, role of the protective coating is to have hottest gases from the combustion chamber than the maximum working temperature of the nickel-based superalloys, being these materials insulating from a thermal point of view. But this is not all, because if we have in mind the environment which would interact with the blade, this environment is coming from combustion gases, where we can have, and that depends on the fuel composition, compounds like sulfur oxide, dioxide or trioxide, or vanadium oxide, as well as oxygen inside the combustion gases, which can give rise, with respect to the nickel-based superalloy, to damages by corrosion. And we can have hot corrosion, which is usually in the range between 700 and 900 Celsius, due to the attack from sulfur trioxide with the formation of sulfides. We can have high temperature oxidations, which is going to happen and be relevant on the nickel-based superalloys due to the presence of oxygen, for temperature which are in around 1000 Celsius. Thus, the use of a ceramic coating is something which is suitable also to reduce the corrosion which would happen on the nickel-based superalloys if the coatings should not be used. We have also another phenomena which, for example, can be relevant according to the composition of the air which is used for having the combustion. Think, for example, to something which is flying on a desertic area, which is erosion. So the ceramic coating can be used also to protect the nickel-based superalloys from erosion phenomena due to solid particles which are present, for example, in the gas stream. And which is the standard solution which is used in order to fabricate the most performing, actually, at the state of the art, to fabricate a thermal barrier coatings, is the use of a composite system which is made from an outer layer of called also top coat, which is partially stabilized zirconia. And you see here where you find on the picture ZRO2, the zirconia, partially stabilized zirconia. Then I will be back in a moment to this concept. Then at the base of the picture, you see you have the substrate that is the nickel-based superalloy. And in between the zirconia and the nickel-based superalloy, it is also used another coating, which is named bond coat, and which is a metallic coating, usually a nickel-chromalic composition, that is a metallic alloys which is made by nickel or nickel cobalt, and then always it is going to exist chromium inside the composition, aluminum and yttria. You see on this picture, on the top of the bond coat, also a sort of black line, which is going to correspond to the so-called TGO, that stands for thermally grown oxides, is usually made by alumina. Well, this TGO is not something existing when we fabricate, that is at a time equal to 0, we fabricate the thermal barrier coatings, but is something which is developed under working conditions. So this is a picture of a thermal barrier coating put on a nickel-based superalloys, showing the existence of the thermally grown oxide alpha alumina. That is, this TBC, this thermal barrier coating, has been tested or has been working in real condition. What we can say looking to this picture, first of all, thicknesses. Well, if you look, we are talking about, you have the white bar here, which is 200 microns. We are talking about the thickness of the ceramic top coat, the partially stabilized zirconia, which is around 300 microns. These 300 microns, they are able to maintain a temperature difference from the temperature value of the combustion gases and the temperature of the nickel-based superalloys in working condition, a difference which is higher than 250 Celsius. So they are more efficient, they are more performing, they are very performing in terms of thermal insulation. This is the main role of the ceramic top coat, that is to act, in this case, as a thermal barrier, that is to act for the gradient of temperature to be established between the temperature of the combustion gases and the temperature of the nickel-based superalloys. But if we see this micrograph of the zirconia, you see a quite relevant number of dot point, or black point, yeah. These black points are voids. That means this coating, according to the existing, actually, fabricating technology, which is the most performing one, and which is the plasma spray technology, they are fabricated, but they show a residual porosity which is around 8 to 10%. And this can represent a drawback for us, because as we said before, we do have also to prevent the nickel-based superalloys from hot corrosion, for example, from attack of sulfur trioxide or from high temperature oxidation. And if we have, as it is, interconnected pores, interconnected porosity inside the ceramic top coat, these gases can flow through the thermal barrier coatings to a reduced extent with respect to the absence of the TBC. I agree with you, but they can flow. And if we do not make something in addition, these gases can go in contact with the nickel-based superalloys and can damage the nickel-based superalloys. So in order to avoid this, we use this intermediate layer, which is the bond coat. And the bond coat, if you see, is made from, in terms of composition, from a first part, which is nickel, which is cobalt, or which can be nickel cobalt. I'll be back in a minute on that. and a second part always existing, which is made by chromium, aluminum, and yttrium. So it is made by elements which have high affinity with oxygen. If we take in mind this, the most, let me say, reactive is aluminum. And so oxygen, which is going to flow through the ceramic top coat, can react with aluminum of the bond coat to form alumina, to form aluminum oxide, thus preventing that the same oxygen, for example, can go in contact with the nickel-based superalloys. This is the reason because of the so-called thermally grown oxide, thermally because it is formed when the temperature is high, that is when the temperature is going to be representing a real working condition, is not existing at the initial time of fabricating the thermal barrier coatings, but is going to be developed during the working condition of the thermal barrier coatings. So this bond coat has a fourth function. That is that to represent an oxidation barrier, that is that to avoid that oxygen could go in contact with the nickel-based superalloys and could damage the nickel-based superalloys. Due to the formation of this thermally grown oxide, which is very dense, also other gaseous species, like for example those which can give rise to the hot corrosion phenomena, are stopped and cannot go in contact with the nickel-based superalloys. Second important function of the bond coat is again related to the composition of the bond coat and is related to thermomechanical stresses. What do I mean? I mean that when we are going to put, generally speaking, a ceramic materials on a metallic materials, think, for example, to put directly the top coat on the nickel-based superalloys, not discussing now about corrosion deterioration, but about mechanical loads. Well, if we rise the temperature of this system, think the engine is going to work, we will have, with respect to the room temperature condition when the engine is off, a dilatation of the materials if we rise the temperature, which is directly linked to the thermal expansion coefficient of the materials itself. Now, the case is that the thermal expansion coefficient of the zirconia is sensibly lower of that of the nickel-based superalloys. And this mismatch in the thermal expansion coefficient can give rise to tensile stress during the heating phase, which are very bad tolerated by the ceramic materials due to the very low value, as we said before, of the fracture toughness of the materials itself. And so we need also to deal with this problem. And dealing with this problem, we will not use, that's the first solution, pure zirconia, but we will use the concept of partially stabilized zirconia. And the most performing, also looking to the economical aspect, solution nowadays is to partially stabilize the zirconia by using from 6 to 8% in weight of another oxide, which is yttrium oxide, Y2O3. Then we will be back on what does it mean partially stabilized. But let me conclude first of all this. So first thing we make is to use a partially stabilized zirconia. Then, if we put in between the top coat and the superalloy a material which can show a thermal expansion coefficient which is higher than the value of the nickel-based superalloys, but still lower, because this is a metallic material, of the ceramic top coat, we have reduced the thermal expansion mismatch, and so we can reduce the thermally induced stresses. And this is the reason because of we use additional reason because of we use the bond coat with this composition. Why with this composition? Because if we have a nickel-based superalloys, we will use a bond coat having a nico-crali or a Ni-crali composition. If instead we should have had a cobalt-based superalloys as a substrate, we would have used a co-crali composition for the bond coats. So the first element or the first two elements, they are going to recall the composition of the superalloy. Then if we look to the other, chromium, aluminum, and yttria, and we put our attention, for example, on yttria, that is true. It's true that the most, let me say, reactive species is aluminum, forming aluminum oxide during exercise. But it is also true that we have met chromium, for example, in high temperature stills, and we remember that chromium is able to react with oxygen to form chromium oxide. Remember, for example, that's not high temperature corrosion, but just to underline the affinity of chromium with oxygen, the passivation state in stainless steel, for example. But it is also true that yttrium, the element yttrium, it also has affinity with oxygen. And so beside the formation of aluminum oxide, which is the external layer, also chromium oxide and yttrium oxide will be formed during exercise. And if we put our attention on yttrium oxide, well, we can have yttrium oxide, and we have it in the formulation of the top coat, and so that we can expect that the bond coat can show during the exercise a thermal expansion coefficient which is intermediate between the value of the top coat and the value of the bond coat. The value of the top coat and the value of the substrate, the superalloy. Thus explaining both the function of the bond coat. Another thing that we must remember, other two things. First of all, if we want to avoid, to be sure that no gas, apart the formation of compact and dense oxide on the surface of the bond coat, could flow through the bond coat and attack the metallic substrate, we should keep the porosity of the bond coat a very, very low value. And if you have a look to this picture, and you see the number, as we said before, of the black dots we have in the top coat, they are not existing on the bond coat. And so this is usually achieved by fabricating the bond coat, I remember to you, not with a plasma spray technology, which belongs to the class of the so-called thermal spray processes, but with another processes always based on spraying, always belonging to the class of thermal spray processes, which is the so-called high velocity oxygen fuel process, HVOF, in which we do have very, very high velocity of particles, so that when the coating is fabricated, the porosity can kept a very low value. So we change the fabrication technology of the bond coat with respect to the top coat, still being inside the thermal spray processes, but looking to HVOF and not to plasma spray. The second thing that we must say is, well, when we have discussed before about chemical reactivity of ceramic materials, we said that they do have low chemical reactivity because they are not subjected to electrochemical corrosion. But I said to you that in some cases, and that depends on the working environment and on the material composition, they can experience, let me say, high temperature corrosion. Well, we have the classes of the ceramic materials, the oxide-based ceramic and the non-oxide-based ceramics. If we use a non-oxide-based ceramic working in an oxidizing environment, that means with oxygen inside, at high temperature, like in these cases, the non-oxide materials will experience an oxidation phenomenon, high temperature corrosion for that. Let's make an example. Let's take, as an example, silicon carbide, which is silicium Si and carbon as two elements. Well, silicon carbide reacting in a different way, but in any case, reacting with oxygen can form silicon oxide, which is the basic constituent of glasses, and then can form carbon oxide or carbon monoxide, that depends on the partial pressure of oxygen, which is also a gas phase, and thus silicon carbide is deteriorated by oxygen at high temperature due to a direct reaction between the constituent elements and oxygen which is present in the working atmosphere. The same applies, for example, can apply for borides as another example. So that we are looking, and we look to the class for this application, thermal barrier coatings, to the class of oxide-based materials, because the top coat is going to work at high temperature in an oxidizing environment. And inside the class of the oxide-based materials, the zirconia is the most suitable one, because zirconia can be, and now we have to discuss about also this, let me say, transformed in order to have not pure zirconia, but with this percent of yttria, to have partially stabilized zirconia. So zirconia, it has oxygen in the formula, so cannot react anymore with oxygen. And this means that oxidation of zirconia, which is an oxide ceramic materials, is not allowed. So these are the main reasons because of this configuration of a thermal barrier coatings. Before talking about the concept of partially stabilized zirconia, the thermal barrier coatings, they are, let me say, subjected, depending on the working condition, to different and very relevant levels of thermomechanical stresses. And if we have a look, for example, with the fly phases, the most stressing, where we need more power, essentially, period of the life of thermal barrier coatings is related to the takeoff of the plane, not so much to the cruise, where we do have a constant speed, but when high maneuverability is requested, for example, and also in the opposite sense, in the terms that we have a very rapid decrease of temperature during the landing and taxi phase. So the most critical phases are takeoff, aerial combat, and landing taxis, where we are asking, for example, for takeoff, and for the intermediate phase, high power to the engine, or where we are going to decrease, because we are putting the engine in a short time in an off mode, we are going to decrease very rapidly the temperature. Zirconia. So let's explain again, I should say, but perhaps in a more detailed way, why we use partially stabilized zirconia. And let's start with pure zirconia, without nothing more added. Well, we can remember, and this is one of the most important surrounding materials for our field in the aerospace. This is the reason because of I'm pointing out all this concept. That in a solid phase, as that which is interesting for us, zirconia is going to exist in three polymorphic forms. Zirconia, even though it is a compound, because it is made by zircon and oxygen, can have allotropic transformation. And so it is stable according to the well-known Bravais lattice into three possible configurations. The first one is the so-called cubic phase, which is stable as crystalline phase in the range between 2370 and 2680 Celsius. 2680 Celsius. It is the melting temperature of zirconia. Then in the temperature range from 1240 and 2370, it is stable in the tetragonal phase, so with a lattice, which is going to be corresponding to the tetragonal arrangement, and at temperature which are lower than 1240 Celsius, zirconia, pure zirconia, is stable with a lattice which is monoclinic. So we call it C phase, T phase, or M phase, depending on the thermodynamically stable phase. And what is the drawback with pure zirconia? The drawback is that the tetragonal to monoclinic or monoclinic to tetragonal, I mean, we do have transformation from tetragonal to monoclinic if you are going to cool. We have transformation of monoclinic to tetragonal if you are going to give temperature, to heat. Is a transformation of the unit lattice which happens with a relevant variation in volume, which is something around 6%. And this volume variation is able to break the material. We do have an increase in value in volume when we are going to look to the transformation from tetragonal to monoclinic, and we do have a decrease in volume when we do have a transformation from monoclinic to tetragonal. And since this transformation temperature is something around 1250 Celsius, and just told to you before, as an average, then we can have also, let me say, higher values for high-performing engine. As an average, the thickness, 300 microns of thickness of zirconia, is able to establish a temperature difference which is around 250 Celsius, I told to you before. If we think very simply that 1000 is the maximum working temperature of the superalloy, we use the zirconia to increase the gas temperature of something which is around 250 Celsius or 300, the same. Well, this means that we are going to think that the working temperature of the zirconia is just around the transformation temperature. And if the transformation is going to occur, the zirconia will break, and if the zirconia will break, we will not have more the thermal protection of the nickel-based superalloy. So we need to do something. And we can solve this by alloying zirconia with other oxides, which are, for example, as they are listed here, magnesium oxide, calcium oxide, or yttria oxide. There are also other solutions like hafnium oxide, for example. And among these possible solutions, to have the best performing answer of the coating for our purpose, we select, because this is the line which gives to us the best performing answer in terms of cost to benefit ratio, yttrium oxide. And so when we are going to put together zirconium oxide with yttrium oxide, in order to understand what is going to happen in terms of thermodynamical stability of the phases, we need to look to the phase diagram. They are binary phase diagram in which we do not have on the vertex here and here the elements like in metallic alloys, but we have the compounds. For example, here we have zirconia, 100% zirconia, and on this axis you see, in this case, the mole fraction is reported, not the weight, but the equivalence is very, very simple. An increasing amount of yttrium oxide, which is put as doping element, as doping compounds inside the zirconia. And so depending on the amount of the yttrium oxide that we are going to use, we can have at room temperature situations in terms of thermodynamical stability which are different from those of pure zirconia. Let's have a look, for example, to this, corresponding to PSZ. Well, what says to us this phase diagrams? That if we are at temperature values higher than this one, number 1, the thermodynamical stable phases are just one, the cubic, you see here, which is stable from this temperature to the melting temperature. If we are going to temperature values which are lower than this one, more or less around 2000s, we have two phases which are stable from a thermodynamical point of view, the tetragonal phase T and the cubic phase C. If we are going to go to a temperature value which is lower than this one, the temperature that we could call 2, which is something around 900, we do have again two phases which are stable from a thermodynamical point of view, that is the cubic phase and the monoclinic phase. So first, when we add, as in this case, yttria stabilized yttria oxide, from a thermodynamical point of view, our materials at room temperature is stable, showing not only one phase, the monoclinic, like in pure zirconia, but cubic and monoclinic. So this means that the tetragonal, if we have in mind a cooling process, which was present in this area of the diagram, more or less has been transformed in monoclinic. Still, the cubic be existing in the forms of cubic. This cubic, zirconia, which is stable at room temperature, still remains cubic when we go here, still remains cubic when we go at temperature values higher than the value T1, this one. And so we say that we have partially stabilized the zirconia because we have a phase which is not going to show any allotropic transformation when we heat again, for example, being cubic at the beginning at room temperature, one phase, and still being cubic till we reach the melting point of the materials itself. This is the reason because we say partially stabilized. Now, on which effect we can rely in order to better motivate the necessity to use the partially stabilized. When we have a look, like in this case, to phase diagram of materials, this applies also for elements, not only for compounds. That's a general concept. Please remember, as I told to you before, by discussing, that they represent thermodynamical stable phases. That is, we give to the materials all the time which the materials requires in order to let the spontaneous transformation to happen to reach the thermodynamical stable phases. And where is the tricks here? The tricks is related to this tetragonal zirconia, which is going to exist at higher temperature value, which is going to be transformed to the monoclinic phase only if we leave to the materials, for example, on cooling, all the time which is necessary to the transformation to happen. But we know because we have experienced this also in metallic alloys. No? Think to the temper designation, for example, that if we make a rapid cooling, starting from a point here, okay, we do not, with a rapid cooling, we do not leave to the materials the time necessary to go towards a thermodynamical, that is an equilibrium situation, because all these transformations are solid transformation, that is, are controlled by solid state diffusion. Thus, if we are here and make a rapid cooling, we do not need to transform the cubic, because the cubic still exists in this area. But we avoid the transformation tetragonal to monoclinic, and we will have at room temperature a cubic phase into our zirconia and a metastable, that is not stable from a thermodynamical point of view, tetragonal phase. And this is the concept on which we rely for the partially stabilized zirconia properties. Why? Because we should be able, and please trust me, we are able, you have a look to this picture, to let this tetragonal zirconia existing here and still being existing in a metastable phase when we use a very rapid cooling, to be in a special form like this, lens-shaped, very fine and very well distributed inside the cubic zirconia matrix. So when we reach this, and this is possible during the fabrication of the thermal biocoatings with the technology that we have, we can rely on another aspect, sorry. Because we have said that when we have the transformation from tetragonal to monoclinic, okay, we do have an increase of volume. And we have related this one thinking to a temperature guided transformation. Well, the tetragonal zirconia existing in the form of metastable zirconia at room temperature is able to transform to monoclinic not only if we are moving the temperature, but if these particles of tetragonals meet areas where the stress concentration is very, very high. And when or where we can expect to have a very high stress concentration, we can expect to have this at a crack tip, where defects inside the coatings, as well as in all the ceramic materials they exist, they are existing, where the stress intensity factor is the highest value. So the stress which is intensified at the crack tip is able to activate the transformation of the metastable tetragonal zirconia to monoclinic zirconia. This is a transformation which still happens with an increase in volume. And the question is, why in this case, this transformation which show again an increase in volume does not give as a result the fracture of the materials itself? Because this increase in volume is related to the single particles, very fine, of metastable tetragonal, and can be tolerated by the materials itself by closing the crack. So recovering, let me say, this volume which is near the crack tip. And the result, so, is that the length of the crack tip is going to be reduced. And this increase in volume, which would cause the breaking of the materials if it would be considered in 100% of the material, all tetragonal transforming in monoclinic or all monoclinic transforming in tetragonal, in this case does not give rise to fracture of the thermal barrier coatings, but give rise to a decrease of the length of the defects. And thus, the results which is going to follow to this is that if the length of the defect is going to be reduced due to the transformation, we do have an increased resistance of the materials itself to crack propagation. And how we do say this? We say that we can expect, and we have it, for partially stabilized zirconia, where stress concentration is going to activate a toughening mechanism, reducing the crack length, we do have a higher value of fracture toughness of the materials, even though it's an apparent fracture toughness because it is related to the closing of the cracks. And if we start with pure zirconia, where the fracture toughness of the materials is something again about 3.5 megapascal per square meter, in the solution that we are going to describe by using a partial stabilized zirconia with 6 to 8% in weight of yttrium oxide, we can reach value of fracture toughness which are near, let me say, 13 or 15 megapascal per square meter, with a very relevant increase in fracture toughness of the materials itself due to this transformation mechanism. And even though 15 megapascal per square meter as fracture toughness of the material is not so high as 40 megapascal per square meter, which we mentioned before for example, aluminum alloys, but we are going to increase of many 100% the value of the fracture toughness of the zirconia top coat, making so this coating not only suitable in order to have a decrease of the working temperature of the superalloy, even by using the bond coat, but also more tolerant, more resistant to crack propagation, thus having a suitable lifetime for the TBC top coat. Obviously, this effect will end when all the tetragonal will be transformed to monoclinic, but it doesn't matter, because if we are talking about this solution, okay, this coating, as well as if we need the TGO, which is going to affect the fatigue resistance of the TBC in the wall, this coating can be removed, and for example, by water jet tools, and can be refabricated on the system. If we want, we can remove also the bond. We have the superalloy not affected by any damages, and it can be refabricated on the blade in order to restart with a duly selected lifetime of the blade itself. So these are the reasons because of we use these ceramic materials in our solution of thermal barrier coating by relying on toughening mechanism induced by stress due to the possibility to fabricate the top coat having a cubic phase, which is stable, with a tetragonal metastable phase dispersed finally inside. And this is possible only if, in our phase diagram, we do have a double phase system, like in the case we put zirconia together with yttrium oxide. If we are here where we have just pure zirconia, what is going to happen from a thermodynamical point of view is what we have said that. So we could also think to have a room temperature all tetragonal phase if we are going to cool from here to here in a very rapid way. But we will not have a second stable phase like the cubic one, which is existing only with yttrium oxide, also with calcium, also with magnesium oxide, but in terms of increase of fracture toughness, yttrium oxide is going to give the best results. And we could do, I was saying, also this, in the case we do not use yttrium oxide, but we will have a massive here tetragonal metastable, and when the transformation from tetragonal to monoclinic induced by stress will be activated, this will be a transformation affecting a large volume of the material itself, thus fracturing the thermal barrier coatings. There are also other applications. I will close the discussion of today on this slide. This is one example outside our field, which is the use, you see here this pink part of ceramic, bulk ceramic materials, in this case Nord coatings, as implants for hip joint replacement. This is also made to some extent by partially stabilized zirconia. In other case, is made by the use of zirconia toughened alumina, aluminum oxide, in which we disperse, we can disperse by using the same concept of before, tetragonal metastable zirconia phase which can be activated in terms of transformation to monoclinic by stress again, thus increasing the fracture resistance of the head of the ceramic implant, increasing, that is, the K1C of the materials itself. And then we will have development now working for gas turbines in terms of massive component, but here we look to ceramic matrix composite materials, and we will start to discuss in our next lecture on this slide. I think that for today we can stop here. So if you have questions, please tell me. I'm ready to answer.
Prof?
Yes.
Avrei una domanda io.
Dimmi, poi te la devo tradurre in inglese, però dimmi.
Ok, no, io in realtà penso di non aver capito bene come che avviene la stabilizzazione dello zirconia, cioè non ho ben capito per quale motivo l'aggiunta poi di un altro ossido,
Ok,
cioè,
ho capito.
mi sono perso un po', ecco.
Va bene, va bene. So I will make the, your colleague was asking to me a better clarification on partial stabilization of zirconia. So I will answer to this question in two ways. First of all, in Italian, so perhaps I can be more clear for your colleague, and then I will repeat in English for students which do not know the Italian language. Allora, in italiano la cosa è abbastanza semplice. Nel momento in cui si ha appunto l'aggiunta di ossido di ittrio, dal diagramma di fase si vede che a temperatura ambiente il sistema solido zirconia-ittria è un sistema bifasico e non un sistema monofasico. Una prima fase che è la fase cubica, la seconda fase che è la fase monoclina in condizioni di equilibrio termodinamico. Fino a qui ci siamo?
Sì, sì.
Ok. Se pensa ad un raffreddamento di equilibrio, io arrivo alla formazione di cubica più monoclina partendo da tetragonale più cubica, che era il pezzo sopra del diagramma di fase. Il che vuol dire che la cubica sostanzialmente era cubica prima e cubica dopo non si trasforma. La tetragonale si deve trasformare in monoclina in condizioni di equilibrio.